There is a fundamental law in thermodynamics that cannot be violated. Heat flows from hot to cold. Energy dissipates. Temperature equalizes over time. An object in space, at a specific distance from the Sun, will reach a predictable equilibrium temperature based on how much solar radiation it absorbs and how efficiently it radiates that energy back into space. We can calculate this temperature precisely using straightforward physics. We have done it thousands of times for asteroids, comets, and spacecraft throughout the solar system. The math always works. The predictions always match observations. Until 3I Atlas. The thermal behavior of this object violates everything we understand about how matter responds to heating in the vacuum of space. And the violations are not subtle. They are not minor discrepancies that fall within measurement error. They are fundamental impossibilities that require either rewriting our understanding of thermodynamics or acknowledging that we are observing something that is generating its own heat. Let me walk you through the thermal anomalies systematically, using only verified observational data from NASA's James Webb Space Telescope, the Hubble Space Telescope, and multiple infrared observatories that have been tracking this object since July 2025. By the end, you will understand why an increasing number of physicists are privately stating that the thermal signature of 3I Atlas is inconsistent with any natural process. The baseline, how thermal physics should work. Before I explain what is wrong with 3I Atlas, I need to establish what right looks like. When a comet approaches the Sun from the outer solar system, it undergoes predictable thermal evolution. At large distances, beyond Jupiter's orbit, the comet is extremely cold. Surface temperatures are typically 30 to 50 Kelvin, which is about minus 240 degrees Celsius. At these temperatures, only the most volatile compounds like carbon monoxide can sublimate. As the comet moves inward toward the Sun, solar radiation intensifies. The surface heats up. At around 3 astronomical units, water ice begins to sublimate when surface temperatures exceed approximately 150 Kelvin. Near perihelion, the closest approach to the Sun, surface temperatures can reach 200 to 300 Kelvin, depending on the comet's albedo and rotation rate. After perihelion, as the comet moves outward, temperatures decrease. Sublimation slows. Eventually, the comet returns to its frozen state. This thermal cycle is completely predictable. It follows the inverse square law. Solar flux decreases with the square of distance. Temperature responds accordingly. We can model this process with extraordinary accuracy using thermal physics equations that have been validated on hundreds of comets. 3I Atlas does not follow this pattern, not even remotely. Anomaly 1. The cold surface paradox. In November 2025, when 3I Atlas re-emerged from behind the Sun after perihelion, the James Webb Space Telescope conducted detailed spectroscopic observations using its near-infrared spectrograph instrument. The spectra showed something that should not be physically possible. JWST detected strong emission lines from carbon dioxide and carbon monoxide. These gases were being produced at high rates, indicating active sublimation from the nucleus. But the surface temperature required to produce that level of CO2 and CO emission was not detected. The thermal infrared observations showed that surface temperatures remained extraordinarily low, close to absolute zero in some measurements. Let me explain why this is impossible. Carbon dioxide sublimes, transitions directly from solid to gas, at approximately 80 Kelvin when exposed to space vacuum. Carbon monoxide sublimes at even lower temperatures, around 30 Kelvin. For these gases to be produced in the quantities observed, large surface areas must be at or above these sublimation temperatures. But JWST's thermal imaging was not detecting those temperatures consistently across the surface. Instead, the infrared data showed a surface that appeared much colder than physics dictates it should be to produce the observed gas emissions. It is like watching water boil while a thermometer shows the temperature is still 30 degrees below the boiling point. The energy accounting does not balance. Either the thermal sensors are giving wrong readings, which is extraordinarily unlikely given JWST's calibration and the confirmation from other infrared instruments, or something is selectively heating subsurface material while keeping the visible surface cold. That requires active thermal management. That requires insulation. That requires controlled heat distribution. Natural geology does not provide those capabilities. Anomaly 2. Bluer than the Sun. Near perihelion in late October 2025, ground-based observers and NASA's SPHEREX mission documented something unprecedented. 3. I-Atlas changed color dramatically. Prior to perihelion, the object appeared reddish in visible light, consistent with dust scattering and organic compounds common in comets. But as it approached closest solar distance, it shifted to blue. Not slightly blue, distinctly blue, more blue than the Sun itself when analyzed spectroscopically. Professor Avi Loeb from Harvard analyzed this color shift and calculated what surface temperature would be required to produce such a blue spectrum through thermal emission. The answer is approximately 5,800 Kelvin. That is the surface temperature of the Sun. For 3I Atlas to glow bluer than the Sun through thermal blackbody radiation, portions of its surface would need to be as hot as the Sun's photosphere. At the distance of perihelion, approximately 1.4 astronomical units from the Sun, no natural heating mechanism can produce surface temperatures anywhere near that value. Solar heating at that distance produces maximum temperatures of a few hundred Kelvin at most, even on a perfectly black surface with zero albedo. To reach 5,800 Kelvin requires internal heat generation on a massive scale. The alternative explanation, which some researchers have proposed, is that the blue color comes not from thermal emission, but from scattering of sunlight by extremely fine dust particles with specific optical properties. But that explanation has its own problems. Producing dust fine enough to scatter blue light preferentially requires energetic fragmentation processes. The particles must be smaller than the wavelength of visible light, meaning tens to hundreds of nanometers. Natural cometary dust production through sublimation typically creates particles in the micron to millimeter size range, which are thousands of times larger. Creating nanoscale dust requires grinding, crushing, or explosive fragmentation, and you need to produce it in vast quantities to create the observed brightness. The energy required to fragment material that finely, continuously, over days and weeks, again points to active processes that natural sublimation cannot provide. Anomaly 3. The concentric thermal layers. In November 2025, enhanced thermal imaging from ground-based adaptive optic systems and orbital infrared telescopes revealed detailed structure in the inner coma of 3I Atlas. The thermal maps showed something extraordinary: highly organized concentric thermal layers surrounding the nucleus. Not random temperature variations, not chaotic heat distribution. Organized rings of different temperatures arranged in perfect circles around the central body. A forensic analysis of these thermal images, conducted using the same methodical standards applied in legal evidence examination, documented this structure in detail. The thermal profile shows distinct temperature bands: a hot central region, a cooler intermediate ring, a warmer outer region, then cooler again. This layered structure is visible consistently across multiple observation dates, indicating it is a persistent feature of the object, not a transient phenomenon. In natural systems, heat diffuses. It spreads out evenly over time. You do not get sharp boundaries between temperature zones unless there are physical barriers preventing heat flow. The concentric thermal layers suggest that 3I Atlas has internal structure that compartmentalizes heat. Insulating layers, thermal barriers, controlled heat distribution systems. You see this kind of thermal architecture in spacecraft and satellites where different components need to be maintained at different temperatures for optimal function. You do not see it in natural comets, which are homogeneous mixtures of ice, rock, and organic compounds with no organized internal structure. Anomaly 4. The missing thermal tail. Every comet that approaches the Sun develops a thermal tail. As the nucleus heats up and begins shedding gas and dust, that material carries heat away from the nucleus. The heated gas and dust forms a plume that extends anti-sunward, away from the Sun, pushed by solar wind and radiation pressure. When you observe a comet in thermal infrared, you should see an elongated thermal signature, hot nucleus, extended tail of warm material streaming away. The tail should be dramatically hotter along the axis, pointing away from the Sun. This is basic physics. This is what we observe on every active comet. 3I Atlas does not show this. Thermal imaging reveals that the heat distribution around 3I Atlas remains rounded and tightly cohesive. There is no elongated thermal plume. There is no directional heat tail matching the antisolar vector. The thermal envelope stays compact and nearly spherical despite active gas production that should be creating an extended tail. This suggests that whatever mechanism is producing the thermal signature is not following normal sublimation physics. If heat were coming from solar radiation absorbed by the surface and driving sublimation, we would see the expected thermal tail. The absence of that tail indicates the heat source is internal and the thermal control is active, maintaining a compact heat distribution rather than allowing it to stream away naturally. Anomaly 5. The thermal gap. Perhaps the most bizarre feature visible in the enhanced thermal imaging is what researchers are calling the quiet ring. Surrounding the hot central nucleus is a distinct zone where thermal emission drops dramatically. A gap, a void, a ring of relative cold between the hot core and the warmer outer layers. This low-density thermal signature has been documented in multiple imaging methodologies. It appears consistently in thermal infrared observations and in visible light imaging of dust structures. The recurrence of this feature across different wavelengths and different instruments strongly suggests it is not an imaging artifact but a real physical property of the object. But how do you create a cold zone between two hot regions? Heat flows from hot to cold. If the core is hot and the outer material is warm, the intermediate zone should have an intermediate temperature, not a minimum. Unless there is active cooling, unless there is thermal management that deliberately removes heat from specific zones while allowing it to accumulate in others. This is exactly what you would design if you needed to thermally isolate a hot reactor core from surrounding systems that need to be kept cooler. You create a cooling jacket, a heat removal system, a thermal gap that prevents waste heat from reaching sensitive equipment. The quiet ring observed in 3I Atlas has the exact thermal signature you would expect from such a system. Anomaly 6. Heat without sunlight. 3I Atlas is currently at approximately 3.3 astronomical units from the Sun as of February 2026. At that distance, solar flux is approximately 1/10 of what Earth receives. Surface heating from the Sun is minimal. Water ice no longer sublimes significantly. Only the most volatile compounds like carbon monoxide should still be active, and even CO production should be declining. Yet 3I Atlas continues to show strong thermal emission. The object is warm, not as warm as it was near perihelion, but far warmer than it should be at this distance based purely on solar heating. Thermal models that calculate equilibrium temperature based on distance from the Sun and assume surface properties consistently predict temperatures lower than what is actually observed. There is excess heat. Heat that cannot be accounted for by current or recent solar radiation absorption. This excess heat requires an explanation. The standard explanation would be that the interior of the comet absorbed heat during perihelion passage and is slowly releasing that stored heat as it moves outward. This is called thermal lag, and it is a real phenomenon, but thermal lag is limited by the heat capacity of the material and the thermal conductivity that determines how fast heat can diffuse outward. For the observed level of sustained warm temperatures at increasing distance, the thermal lag calculations require the nucleus to have thermal properties that do not match any known cometary composition. You would need extraordinarily high heat capacity to store enough energy during perihelion. You would need extraordinarily low thermal conductivity to prevent that heat from escaping quickly. Those two requirements contradict each other. High heat capacity typically correlates with materials that also conduct heat well, like metals. Low conductivity correlates with insulators like ice and porous rock, which have low heat capacity. Finding a natural material composition that satisfies both requirements simultaneously to match the observed thermal behavior is essentially impossible. The simpler explanation is ongoing internal heat generation. Anomaly 7. The selective heating puzzle. Perhaps the most compelling evidence that the thermal behavior is not natural comes from the pattern of which volatiles are being released at which times and distances. CO2 and CO emissions began when 3I Atlas was still far from the Sun. At distances where solar heating should not be sufficient to sublimate those compounds from a cold surface. Water production began suddenly and dramatically near 3 astronomical units, earlier and more intensely than thermal models predict. Then, curiously, the ratio between different volatiles changed over time in ways that are difficult to explain through passive solar heating. Early observations showed CO2 dominating the emissions. Later observations showed water becoming dominant. Then carbon monoxide increased again. This is not the pattern you expect from a rotating nucleus, with ice deposits being heated randomly as different areas face the Sun. This looks more like selective activation of different chemical reservoirs at different times, like venting from storage tanks, like controlled release from pressurized containers. You activate CO2 first for initial trajectory adjustments. You switch to water for sustained activity and dust production. You use CO for final maneuvers. I am not asserting this is definitely what is happening. I am pointing out that the observed pattern of volatile release matches this scenario better than it matches passive solar-driven sublimation. The energy budget problem. Let me summarize the fundamental thermodynamic problem with 3I Atlas. Energy in must equal energy out plus energy stored. Solar radiation provides the energy in. This is calculable based on distance from the Sun and surface area exposed. Energy out is thermal radiation back into space, plus kinetic energy carried away by ejected gas and dust. This is measurable through infrared observations and spectrographic analysis. Energy stored is the heat that accumulates in the interior. This is limited by heat capacity and constrained by thermal conductivity. For normal comets, this energy budget balances. Input from sun equals output through radiation and sublimation. For 3I Atlas, the energy budget does not balance. The object is producing more thermal energy and more gas than solar input can account for, especially at large distances where solar heating is weak. Multiple research teams have attempted to construct thermal models that match the observations using only solar heating and various assumed material properties. These models consistently fail. You cannot get enough heat into the interior during perihelion to power the observed sustained activity afterward. And you cannot get the interior hot enough to produce the observed emissions while keeping the surface as cold as the thermal imaging indicates. The discrepancy is not small. We are not talking about 10 or 20% more heat than expected, which could potentially be explained by measurement uncertainties or slightly wrong assumptions. We are talking about factors of 2 to 5 more thermal energy than solar heating can provide. That is not an error margin. That is a fundamental violation of energy conservation unless there is an internal heat source. What generates internal heat? If we accept that 3I Atlas has internal heat generation, what could the source be? There are only a few possibilities for natural internal heat in a comet-sized object. Radioactive decay. Long-lived radioactive isotopes like aluminum-26, potassium-40, and uranium-238 generate heat as they decay. This is the primary heat source for Earth's interior. But radioactive heating produces very small amounts of power spread throughout the volume of an object. For a body the size of 3I Atlas, estimated at a few kilometers in diameter, radioactive heating would produce perhaps a few watts total. The observed excess thermal emission indicates power generation in the kilowatt to megawatt range, millions of times more than radioactive decay can provide. Chemical reactions. Exothermic chemical reactions can release heat. This is how explosives work and how some organisms generate warmth. But sustaining chemical heat generation for months requires a continuous supply of reactive materials, and the reactions would consume the reactants, leaving behind reaction products that would be detectable spectroscopically. No evidence of such ongoing large-scale chemistry has been detected. Tidal heating. When an object passes close to a massive body like the Sun or a planet, gravitational tidal forces can flex and deform the object, generating heat through friction. Jupiter's moon Io is the most extreme example, with tidal heating so intense it drives continuous volcanic activity. But 3I Atlas did not pass close enough to the Sun for tidal heating to be significant, and it has not yet reached Jupiter. The amount of heat that could have been generated through tidal flexing during perihelion is far too small to account for observed temperatures months later. So natural heat sources are insufficient, which leaves artificial heat sources. Nuclear reactor. A small fission reactor could generate sustained power for years. The thermal signature would be a hot core radiating waste heat that must be managed and dissipated. This matches what we observe. Chemical energy storage. Advanced batteries or fuel cells could store energy collected from sunlight or generated through nuclear processes, then release that energy as needed for propulsion or other systems. This could explain selective heating and controlled volatile release. Exotic physics. Any sufficiently advanced technology might employ energy generation or storage mechanisms we do not currently understand. Fusion, antimatter, zero-point energy, concepts that appear in theoretical physics but that we have not successfully harnessed. I am not claiming any of these artificial heat sources is definitely present in 3I Atlas. What I am claiming is that the thermal observations require internal heat generation that natural processes cannot provide. And once you require internal heat generation, you are implying technology. The thermal management architecture. If 3I Atlas is generating internal heat, it must also manage that heat carefully. Too much heat and internal systems fail. Electronics fry. Structural materials deform. Too little heat and chemical processes slow or stop. Fluids freeze. Systems become sluggish. The thermal architecture visible in the enhanced imaging, the concentric layers, the quiet ring, the selective surface heating, all suggests sophisticated thermal management. Hot core, where power is generated. Insulating layer to contain that heat and prevent it from reaching the outer structure. Cooling systems that remove excess heat and radiate it to space through specific surfaces. Selective heating of volatile reservoirs when propulsion or gas production is needed. This is not speculation about what such a system might look like. This is description of what the thermal imaging actually shows. Organized heat distribution, compartmentalized temperature zones, controlled emission patterns. These are the signatures of engineered thermal systems, not natural geology. The silence from NASA. Now I need to address the elephant in the room. If the thermal signature of 3I Atlas is as anomalous as I am describing, if it genuinely requires internal heat generation that violates natural explanations, why has NASA not made an official statement about this? Why are we learning about these thermal anomalies through analysis of published data rather than through press conferences announcing a potential technological object? The answer, I believe, is the same as it has been for every other anomaly associated with 3I Atlas. Announcing that an object shows thermal signatures consistent with internal power generation is essentially announcing that it is artificial. That triggers all the consequences that institutions are desperately trying to avoid or manage carefully. So instead, they release the observational data quietly. They publish scientific papers with carefully neutral language. They describe the observations as unusual or unexpected without explicitly stating the implications. And they hope that the scientific community and attentive public will gradually reach the conclusion independently so that when official acknowledgement finally comes, it feels like confirmation rather than revelation. But the thermal data is now public. JWST observations are archived. Ground-based infrared imaging is published in preprint repositories. Anyone with the technical background to analyze thermal physics can download this data and reach their own conclusions. And increasingly, those conclusions are converging on the same answer. 3I, Atlas is generating internal heat that solar radiation cannot account for. The thermal signature shows organized structure and management incompatible with natural processes. The energy budget does not balance without an internal power source. March 16th, the thermal test. 24 days from now, 3I Atlas will pass Jupiter at the Hill radius. That encounter provides another opportunity to test the internal heat hypothesis. If the object has substantial internal heat generation, that heat will affect how it responds to Jupiter's gravitational field. A purely passive cold object will respond only to gravitational forces, but a warm object has thermal expansion, internal pressure from heated volatiles, and potentially active venting that can provide thrust. The trajectory during the Jupiter encounter will be affected by all these factors. If 3I Atlas behaves thermally like a cold passive object despite showing warm temperatures beforehand, that would be a contradiction requiring explanation. If it behaves thermally like a warm active object, showing trajectory perturbations from outgassing or other thermal effects, that provides additional confirmation of internal heat. And if the thermal emission changes during the encounter, either increasing or decreasing in response to Jupiter's gravitational stress or changing distance from the Sun, that will provide valuable data about the heat source and thermal architecture. Multiple infrared observatories will be watching. JWST will likely conduct additional observations if possible. Ground-based thermal imaging will track temperature changes throughout the encounter. The data will either clarify the thermal mystery or deepen it further. But one thing is certain: the temperature anomaly of 3I Atlas is real. It is documented, it is reproducible across multiple instruments and observation techniques, and it defies every natural explanation we have attempted to construct. Heat is being generated inside this object in quantities that solar radiation cannot provide. That heat is being managed and distributed in organized patterns that natural geology cannot produce. And the energy budget only balances if you include an internal power source. In physics, when your observations contradict your assumptions, you must change your assumptions. The observations of 3I Atlas contradict the assumption that it is a natural comet. Perhaps it is time to change that assumption and consider what else might be traveling through our solar system, generating its own heat, managing its own thermal signature, and actively controlling its behavior in ways that natural objects simply cannot.